We should be live. It's testing our audio. Hopefully we're using the correct microphone. Let's jump straight into it. We have this video of a person having a seizure. It was published as part of the paper. We'll go over the paper later on, but let's actually try something hopefully interesting. So the video has the EEG on 20 something electrodes, 1020 EEG, pretty standard stuff, and we have a video of a patient as well. Now we will see how an AI agent, a Gemini to be more specific, is able to review this video. But what we will do is we will actually hide the video, and we will get the AI agent just look at the EEG alone. Well, we'll try to see if you can actually explain what is it we are looking at. Might just get rid of the video. Get rid of the video, and we'll start it in the beginning. The video doesn't have audio. Okay, it has some weird thing in there. Okay, so we have the video starting about here. So we have this. Actually, yeah, let's start it from here. And let's bring in an agent. We'll share the screen with Gemini. Let's see how we go. Share this video. Okay, can you see the video? Can you see the video on the screen?
Yes, I can see a video. It looks like it's displaying EEG readings with various lines representing different brainwave activity.
Okay, one sec. I'm actually having trouble with my audio. One sec. Okay, let's start again. Let's start again.
Yes, I can see a video. It looks like it's displaying EEG readings with various lines representing different brainwave activity.
Okay, nice. Can you give us a bit more details as to what the recordings are?
The recordings appear to be electroencephalogram data, or EEG, showing brainwave activity. There are multiple lines, each representing different electrode placements on the scalp, capturing electrical activity from the brain. The lines are displaying various wave patterns, which can be used to assess brain function. Additionally, at the bottom of the screen, there are lines showing EKG readings, indicating the heart's electrical activity.
Okay, and what's MKR plus, MKR minus, do you know?
The MKR plus and MKR minus indicators at the bottom likely refer to markers or events identified in the recording. These markers might be used to highlight specific points in the data, such as significant wave changes or events that occurred during the recording. They help in analyzing the data more precisely.
Okay, so I'm playing the video now. Can you explain what's coming? Can you see what's coming in the video? What's happening now?
The video is showing the EEG readings progressing over time. There are some changes in the wave patterns, particularly in the red lines at the top, where the waveforms become more prominent and irregular. This could indicate changes in brain activity. The EKG readings at the bottom also continue to show the heart's electrical activity.
Yeah, and can you predict what's happening? So if you had a video of the patient having the EEG recording, what will be happening in the video?
If a patient were having a seizure during this EEG recording, you would likely see significant changes in the brainwave patterns. There would typically be abnormal, synchronized, and high-amplitude electrical activity, often appearing as sharp spikes or wave discharges across multiple EEG channels. These patterns are indicative of the chaotic and excessive electrical activity in the brain during a seizure.
Okay, can we stick to the current recording that you see on the screen? The squiggles there, the larger activity, the darker regions, what do you think they are? Assuming you are an EEG expert, what are they?
Based on the current recording, those larger wave patterns or darker regions could represent various electrical activities. They might be artifacts, such as muscle tremors or eye movements, or they could be significant brain activity, like epileptic discharges, depending on their shape and location, or even normal brainwave patterns during specific states of consciousness. A detailed analysis by a trained expert is necessary to interpret them accurately.
Okay, can you just pretend for this exercise to be an EEG expert? Can you tell me where my mouse cursor now, hopefully you can see my mouse cursor, is this activity EMG or not?
Based on the movement of the mouse cursor and the appearance of the activity in that region, it looks like it could be EMG artifact. EMG, or electromyography, reflects muscle activity, and it often appears as faster, more irregular waveforms compared to brainwave activity. The characteristics of the waveforms in that region are consistent with muscle activity rather than brain activity.
Okay, let's move on. So let's assume this is muscle. What's happening right now as the signal progresses, as the recording progresses? Can you also mention the difference? What do you think the difference is between red and blue recordings?
As the recording progresses, there are various changes in the EEG waveforms. You can see some increased activity in both the red and blue recordings, with more prominent wave patterns appearing. The difference between the red and blue recordings likely represents different electrode placements on the scalp, capturing brainwave activity from different regions of the brain. The variations in the wave patterns between these channels can provide information about the spatial distribution of brain activity.
Okay, and can you be more specific? What's the difference between red and blue?
The primary difference between the red and blue recordings appears to be the location of the electrodes on the scalp. Different electrode placements capture brain activity from different regions, leading to variations in the waveforms observed. The red channels might be recording from frontal regions, while the blue channels might be recording from posterior regions or other specific areas, resulting in the different wave patterns you see.
Okay, for the sake of this exercise, can you be very, very specific? So you're like an absolute expert in EEG recordings. Can you look at the labels of each channel and tell again exactly what's the difference between red and blue?
Based on the channel labels, the red recordings primarily represent activity from frontal and temporal regions on the left side of the scalp, such as FP1 to F3, F3 to C3, C3 to P3, and FP1 to F7, among others. The blue channels, on the other hand, capture activity from central and posterior regions, including C4 to P402, FP2 to F8, and T8 to P8, among other locations. The differences in the waveforms are due to the distinct brain activity patterns picked up by these varied electrode positions.
Okay, that's very nice. What's the current, again, looking at the labels of each channel, what's the current montage that is being used? Can you explain what it is and just make make a guess which montage is being used?
Based on the channel labels, it appears to be a longitudinal montage, also known as a referential montage. In this montage, each channel records the difference in electrical potential between two adjacent electrodes in a specific chain, or line, relative to a common reference. This configuration allows for the assessment of brain activity across different regions, emphasizing the electrical gradients between electrodes.
Okay, this is really nice. So I'm playing the rest of the video. What's currently happening? What's coming in the signal? Can you again continue pretending being an EEG expert and tell me what's happening?
As the recording progresses, there are some significant changes in the EEG signals. You can observe periods of increased amplitude and frequency in both the red and blue channels, which might indicate increased brain activity or artifacts. There are also some brief episodes of more rapid, high-amplitude waveforms, particularly in the red channels, which could suggest specific brainwave events or muscle artifact. The blue channels also show periods of increased activity, sometimes with more distinct wave patterns. Overall, the signal. So, in this longitudinal montage, you're seeing the electrical potentials measured between neighboring electrodes, which helps to localize brain activity along the scalp. The different patterns in the waveforms reflect the varying electrical activity generated by different brain regions. This type of montage is useful for identifying the spatial distribution of brain activity and can be helpful in detecting abnormalities in specific regions.
Okay, and what do you think we are mainly seeing? What's the signal indicates?
The signal indicates various brainwave patterns along with some artifact, likely muscle activity. The different waveforms in the different channels suggest varying brain activity across different regions of the scalp. The presence of faster or regular activity, particularly in some channels, indicates the presence of muscle artifact.
Okay, I'll keep playing the video. Can the next screen? What's happening now? Can you indicate the details and also the difference between the different what's happening on what's specifically happening on different channels? What's the difference is?
From the video, I can see different brainwave patterns evolving across the various channels. Some channels show more rhythmic and organized activity, while others display faster, more chaotic waveforms, which could be due to muscle artifact or different brain activity states. The variations in amplitude and frequency across the channels indicate localized brain activity patterns. The longitudinal montage allows for comparison between adjacent electrodes, helping to pinpoint the source of these activities.
Okay, I'll keep playing the video. What's happening now? Is it mainly muscle or is there something else going on?
It appears there's a combination of muscle artifact and brain activity. The very fast, irregular waveforms in several channels are characteristic of muscle artifact. However, there are also slower, more rhythmic patterns in other channels, which indicate typical brainwave activity. It's important to differentiate between these two types of signals to accurately interpret the EEG data.
Okay, I keep playing the video. What's coming? Can you tell if potentially there is no more EMG? Is there anything else going on? Can you tell?
From the video, it looks like the muscle artifact has significantly decreased or is much less prominent now. The brainwave patterns appear more rhythmic and rhythmic. There might still be some subtle activity, but it looks like the focus is more on the brain's natural electrical activity now. It's important to continue observing for any changes or anomalies in the waveforms.
Okay, that's a bit weird. Wait a sec. So, can you look at this time period, time window over here, and what difference does it make um, compared to this image here? What difference are we seeing? So second 12 compared to second 1 minute and 40 seconds. What's the difference between the two states?
Comparing the time periods, the earlier segment showed more significant muscle artifact, characterized by fast, irregular waveforms, especially in some channels. In the later segment, the muscle artifact appears reduced, and the brainwave patterns are more regular and discernible. This suggests a clearer view of the brain's underlying electrical activity with less interference from muscle movement.
Okay, let's keep going. We'll play it from this point onward. Can you tell what's going on? What's happening here and what changed?
Based on the current view, the EEG activity appears to have calmed down significantly. The waveforms are much more regular and less erratic, indicating a reduction in muscle artifact and a clearer recording of brain activity. It looks like the person is now in a more relaxed state, compared to the earlier segments with more noise and movement.
Okay, except noise. Is there anything else going on in the signal? Can you keep looking at it? And is it baseline? Do you think it's baseline or not?
Yes, based on the reduced noise and more regular waveforms, the current signal appears to be a much cleaner baseline recording. It seems like the person is in a relaxed state with minimal muscle movement, allowing for a clearer representation of the brain's intrinsic electrical activity.
Okay, are you able to tell what the frequency of the brain activity, say, on the bottom channel there?
The brainwave activity on the bottom channel appears to be in the alpha range, typically between 8 and 12 hertz. The waves are relatively rhythmic and organized, which is characteristic of alpha wave activity, often associated with a relaxed but awake state.
Are there any artifacts in the signal?
No, in this current time window, the signal appears relatively free of artifacts. The earlier segments had noticeable muscle artifact, but the current view shows much cleaner brain activity with minimal interference.
Except the muscle artifact, are there any other types of artifacts? Also, what have changed now?
Besides muscle artifact, there aren't any significant other types of artifacts in this view. The signal is now much clearer, and the primary brainwave activity is more discernible. The change is mainly a reduction in noise and a cleaner recording of the underlying brain activity, suggesting a more relaxed state of the subject.
Okay. Are you sure about that? Are you sure it's baseline and nothing else is going on? Can you double check? Well, there is muscle now, but before, was there anything happening before?
You're right. Looking closely again, there was a brief period of increased muscle artifact just before the current clean segment. It seems the baseline recording was interrupted by some muscle tension, but now the signal is much clearer again. Thanks for pointing that out.
Okay, that's interesting because essentially it was not able to make a diagnosis. Yeah, which is quite interesting. Quite interesting. Yeah, so I wonder what it will able to do if it had the video of the patient as well. But then some things are pretty obvious. Should be pretty obvious. If we hide the patient again. Let's extract two images real quick. Let's extract, yeah, this one, which meant to be baseline. Then we have some muscle, and then we have this one here. Should be fairly obvious what it is. Let's see if another model can get it right. One sec. So we have, let's do this too. Yeah, that's super weird. Yeah, I think we are in business. So we have these 10 files. Okay, we have these 10 files. Okay, we have these 10 files for you to review. Assuming you are an expert neurologist, using this data, can you make a diagnosis? Okay, let's see. So let's do Gemini 2.5 Pro, whatever version of today, 14th June. They're meant to be in order. Let's bring a prompt engineer. Okay, can you quickly review and discuss what's the agent doing? What's happening on the screen?
The agent is currently analyzing 10 EEG files, trying to identify patterns that might suggest a diagnosis from a neurological perspective. It's focusing on detecting muscle artifacts and patterns related to bruxism, while acknowledging the limitations of making a full diagnosis based on static images.
Okay, what else is it doing?
It's refining its analysis by looking at the frequency and spatial distribution of muscle artifacts, correlating them with the user's clues about bruxism. It's also noting the absence of patterns indicative of night terror events. The agent is carefully constructing its response, integrating all observations, and emphasizing the limitations of the data.
Okay, I keep scrolling down on their response. What else are they trying to do?
It's organizing its findings into a clear structure, focusing on presenting a detailed assessment of muscle artifacts and their correlation with suspected bruxism. It's also ensuring the report includes a disclaimer and maintains an educational tone, emphasizing the limitations of using static images for diagnosis.
Okay, what's their response is?
The agent's response is providing a detailed analysis of the EEG snippets, highlighting rhythmic muscle artifacts consistent with sleep bruxism. It describes the morphology and location of these artifacts, while also explaining the limitations of the data and the need for further clinical information for a complete diagnosis.
Okay, keep going.
It's further elaborating on the findings, detailing the specific timeframes where the muscle artifacts are observed, and explaining their characteristics. The agent is also reiterating the need for more comprehensive data, like the complete EEG data and clinical information, to make a definitive diagnosis.
But we did provide the complete EEG data. What else are they saying?
The agent is acknowledging the presence of rhythmic muscle artifacts, which are characteristic of sleep bruxism. It's also mentioning the associated features, like the disruption of the background EEG rhythm and tachycardia, suggesting a brief arousal from sleep. The agent is emphasizing that these findings are consistent with sleep bruxism, but still require further clinical correlation.
Okay, what else are they saying?
The agent is also discussing the background EEG rhythm and sleep staging, noting that the activity appears consistent with lighter stages of sleep, rather than deep sleep. It also mentions that the images labeled night terror EEG show a mixed frequency EEG, but not the classic pattern typically associated with night terrors. The agent is evaluating other potential diagnoses, like epilepsy and night terrors. It notes that there are no clear epileptiform discharges to suggest epilepsy, and the EEG pattern doesn't match the typical night terror pattern, which typically arises from deep sleep. The agent in conclusion that the primary findings are most indicative of sleep bruxism. The agent is providing an impression and potential diagnosis, suggesting that the findings are highly suggestive of frequent and significant sleep bruxism, associated with multiple arousals from sleep. It also mentions potential consequences of sleep bruxism, such as jaw pain, dental damage, and fragmented sleep. Finally, it recommends a full polysomnogram review and ruling out other sleep disorders to confirm the diagnosis. No, the agent is not suggesting epilepsy. It note specifically mentions that there are no clear epileptiform discharges that would suggest an epileptic seizure. The primary findings are more consistent with sleep bruxism. The agent is recommending a full polysomnogram review to confirm the diagnosis and rule out other sleep disorders such as obstructive sleep apnea, which can cause arousals. It's also suggesting that a thorough clinical history and dental examination would be valuable for accurate diagnosis and treatment planning. Based on the provided images, the agent's impression is that the findings are highly suggestive of frequent and significant sleep bruxism associated with multiple arousals from sleep. However, it emphasizes that a formal diagnosis requires a comprehensive evaluation, including a full polysomnogram and clinical correlation.
So are they sure it's not epilepsy?
Yes, based on the EEG snippets provided, the agent's assessment is that there is no clear evidence of epilepsy. The findings are primarily indicative of sleep bruxism. Yes, I'm sure. The agent's analysis clearly states that there are no clear epileptiform discharges that would suggest an epileptic seizure. The observed patterns are consistent with sleep bruxism, rather than epilepsy. The agent is reevaluating your question, reinforcing its initial assessment that the findings are more suggestive of sleep bruxism than epilepsy. It's further explaining the specific characteristics of the EEG patterns, like the spiky morphology and location over the jaw muscles, that strongly indicate muscle artifact associated with bruxism. The agent is further clarifying its diagnosis, emphasizing the distinction between muscle artifact and epileptic activity. It's preparing to provide a more detailed explanation, likely including a comparison table to highlight the differences in morphology, location, and clinical context. The agent is providing a detailed comparison between the observed patterns and typical epileptic seizure activity. It's highlighting the differences in the source, appearance, and location of the electrical activity, explaining why the observed patterns are indicative of muscle artifact from bruxism, rather than epilepsy. Certainly. The agent notes that the observed patterns originate from muscles outside the skull, specifically the jaw muscles, whereas epileptic seizures originate from brain neurons. The observed patterns have a high frequency, spiky appearance, and are localized directly over the jaw muscles, unlike the evolving patterns seen in epileptic seizures. Additionally, the observed activity stops abruptly when the muscle clenching stops, whereas a true seizure is typically followed by a period of post-ictal slowing, which was not observed. The agent is using an analogy to further explain the difference. It compares the muscle artifact to the sound of an engine heard from outside a car, while comparing an epileptic seizure to a person shouting from inside the car. This analogy highlights that the observed activity is originating from external sources, the muscles, not from the brain itself. The agent is examining a new image and trying to determine if it contains the same data as the previous images. It's noting visual differences in color, annotations, and montage, and is looking for ways to compare the underlying EEG signals despite these visual discrepancies. The image appears to show EEG waveforms, similar to the previous images, and the agent is trying to determine if the underlying data represents the same events or different ones. The agent has concluded that the new image contains different EEG data than the previous images. It notes differences in color, channel counts, annotations, and the presence of different types of artifacts, such as eye flutter and 60 Hz interference in the new image. Therefore, it determines that the data is not the same, and likely comes from a different source, such as a textbook or scientific paper. While it's possible to have different montages of the same data, the agent's analysis indicates significant differences beyond just the arrangement of channels. The differences in color, annotations, and the presence of distinct artifacts suggest that this is a completely different EEG recording, not just a different presentation of the same data. Sure. How about asking, do these new EEG images represent the same data as the previous ones, or are they from a different recording? Based on the agent's analysis, it's unlikely that the new image represents the same data with a different montage. The agent identified significant differences. Okay, here's a question. Could the variations in artifacts, color, and annotations between these EEG images be accounted for by a different montage of the same data? Or do they indicate a completely different recording? The agent is carefully considering your question about the possibility of a different montage. It's examining the nature of montages and how they affect the appearance of EEG signals, particularly in relation to identifying artifacts. The agent is working to clarify how montages can alter the visualization without altering the underlying data, and how to distinguish between different signal sources, like bruxism and electrical interference. The agent is explaining that the key difference lies in the types of artifacts present. It clarifies that montages only change how the data is displayed, not the underlying signals themselves. Since the two recordings show distinct types of artifacts, like bruxism and 60 Hz interference, it indicates that they originate from completely different events and sources, regardless of the montage used.
Okay, picture this. You see someone, and suddenly their eyelids start fluttering really fast, involuntarily.
Mm-hmm.
That specific kind of defining feature is called eyelid myoclonia, or EM. And for years, well, this has been the absolute cornerstone for diagnosing a specific type of epilepsy called EEM epilepsy with eyelid myoclonia. You sometimes hear it called Jevons syndrome, too. Welcome to the deep dive. Our whole mission here is to take a stack of information, could be the latest research, articles, notes you've sent in, and just cut through all the noise.
Yeah.
We want to pull out the most important bits, the surprising insights, and help you understand what it, really means.
Yeah.
Today we're diving into a really fascinating scientific paper. It takes a pretty critical look at how we've traditionally understood EM, and it points towards a surprising and potentially pivotal part of the brain.
That's exactly right. The paper we're digging into is titled Unmasking the Role of the Occipital Lobe in Epilepsy with Eyelid Myoclonia. It's a brief communication, but quite impactful, published in the journal Epilepsia just this year, 2025. It's by Ricci and colleagues, drawing from work mainly at the Danish Epilepsy Center and some collaborating places.
And our goal for this deep dive is to really examine this research critically. We want to understand how these findings might potentially challenge the standard definition of EM. We're zeroing in on the brain's occipital lobe, that area way at the back, the one we usually link with processing vision. We'll look at why these findings are important, both for diagnosis and just for our basic understanding of this condition. It's really about peeling back the layers on something that seemed pretty straightforward and discovering some unexpected complexity, and hopefully doing it in a way that makes the neuroscience kind of fun to learn about.
Exactly. So we'll first sort of ground ourselves in the established understanding of EM. Then we'll dive into the methods and, importantly, the surprising findings of this study. And finally, we'll explore the implications they discuss, which are pretty significant.
Okay, so let's rewind a bit then. Before this paper, what was the standard picture of EM or Jevons syndrome? How is it defined?
Well, based on the criteria from the International League Against Epilepsy, the ILA-EM has long been classified as a genetic generalized epilepsy, or GGE. The thinking was that the seizure activity starts everywhere, involving both sides of the brain right from the get-go.
Generalize, okay.
Right. It typically kicks off in childhood. It's much more common in females. And like you said, the absolute hallmark is that eyelid myoclonia, the fluttering seizures, which are almost always triggered by closing the eyes.
Got it. And what else usually comes along with it?
Patients often have these very brief staring spells, what we call absences. Sometimes they happen right after or even during the eyelid fluttering. And on an EEG, the brainwave recording, you see these generalized epileptiform discharges. These are basically abnormal bursts of electrical activity spread across the whole brain. And photosensitivity, that sensitivity to flashing lights that can trigger seizures, that's also really, really common in EM.
Okay, now here's the part that this new paper really gets into, and it's like a fundamental rule in the traditional diagnosis. Historically, if a patient had focal seizures starting in one specific spot in the brain, that would actually rule out an EM diagnosis.
Exactly. The ILA criteria drew a really firm line there. There was even an international expert panel that recommended if focal seizures did show up, clinicians should probably reconsider the EM diagnosis entirely. It was meant to be a clear split, generalized, not focal.
Right, a clear boundary.
Which sets the stage perfectly for the question Ricci and colleagues were tackling. They noticed that despite this very strict rule, there had been some reports floating around, maybe anecdotal, maybe smaller studies, kind of hinting that maybe the occipital lobe, that visual area back there, does play a bigger role in EM than the traditional definition allowed for.
Oh.
So they basically asked, could focal seizures, especially ones starting in the occipital lobe, actually be happening in patients who otherwise look like classic EEM cases?
That's a pretty bold question, really challenging the established thinking. So how did they try to answer that? What was their approach?
They did a retrospective study, so they went back through medical records and, really importantly, the video EEG recordings. They looked at 21 patients who'd been diagnosed with EM at the Danish Epilepsy Center over about 5 years. And they were careful. They only included patients who definitely met the standard mandatory ILA criteria for typical EM features.
So not borderline cases. These were patients who by the book, shouldn't have focal seizures, according to that old definition. Could you give us a quick snapshot of this group?
Sure, it was relatively small, 21 patients, but clinically very well described. Aligning with what we know about EM prevalence, the vast majority were female, 20 females, just one male.
Right.
Average age when studied was 21, but the seizures typically started much younger, around age 7 or so. Most had normal or maybe borderline intellectual function, though a few did have other things going on, like ASD or ADHD. And unfortunately, like you see in many epilepsies, most were already on multiple anti-seizure medications.
Okay, so they took this group, typical EEM, supposedly no focal seizures allowed, and did this deep dive with video EEG, recording brainwaves and video simultaneously. What did they actually find when they looked closely at that EEG data? Let's get into the results.
Well, first, they confirmed what you'd expect, right? All 21 patients showed those generalized epileptiform discharges on their EEG. Saw them when awake, saw them during sleep. That fits the definition of generalized epilepsy in EM perfectly.
Right, check. Standard stuff. But then came the twist.
Yes, and this is where it really pushes back against the traditional view. Despite EM being classified as purely generalized, they found that a huge majority, actually 90% of these patients, also had focal epileptiform discharges on their EEG recording.
90%? Wait, 90?
Ah.
That's dramatically higher than the 0% the old definition would lead you to expect.
Yeah, absolutely. It's a striking number. And critically, they looked at where these focal discharges were popping up. They weren't just random. They were frequently found in the posterior brain regions. That squarely includes the occipital lobe.
Not back of the head.
Exactly. These posterior focal discharges were seen in 47% of the individual EEG recordings they looked at across the group. And interestingly, they were often bilateral, showing up on both sides of the back. They did see some focal discharges elsewhere too, but the posterior activity was really prominent.
So not only were focal discharges common, but they were kind of clustering right there in the occipital area.
Yeah.
Did this connect back to that key trigger for EMM closing the eyes?
Yes, and this is another really key piece of evidence linking the occipital lobe to the core EM thing. Eye closure, as we said, is the classic trigger for the eyelid myoclonia and the generalized discharges in EM.
Right.
In this study, while, yes, all patients showed generalized discharges right after eye closure, a really significant number, 76% of them showed a focal posterior discharge that consistently came just before the generalized activity on the EEG.
Whoa, okay. So it's like the abnormal electrical storm was actually starting locally in the back of the brain first, and then it quickly spread out to become generalized.
That's exactly the pattern the EEG suggested. The occipital area, or maybe nearby posterior regions, seemed to be the first place to fire off abnormally, and then that activity propagated, spreading to involve wider brain networks. The paper describes this preceding activity often as rapid spikes, or this specific fast rhythmic pattern they call spiky beta activity. It suggests very rapid, synchronized, abnormal firing in that specific spot.
Okay, so seeing focal discharges before the generalized ones is one thing. But the traditional rule was about focal seizures. Did they actually manage to document any clear-cut focal seizures in these patients who otherwise fit the typical EEM picture?
This is probably one of the single most compelling bits of data in the whole paper. It's in their case report for patient 1. This patient had all the textbook features of EM, met all the standard criteria, everything. But, and this is crucial, during the long-term video EED monitoring they were doing, to better characterize their eyelid myoclonia and absences, they actually captured and recorded a real focal seizure.
A documented focal seizure. In someone who, by definition, shouldn't have one if they truly have EEM.
Precisely that. The seizure itself was described as having pretty subtle clinical symptoms, so not like dramatic shaking or total loss of consciousness, but maybe brief, slight changes in awareness or perception, and it was followed by amnesia, so the patient couldn't remember it. But the EEG, crystal clear. It showed the seizure activity starting in the right occipital region and then spreading forward to other brain areas.
Wow.
So having this single documented focal event in a patient with otherwise undeniable typical EM features, that's really powerful evidence against that strict exclusion rule.
That certainly punches a hole in the old rule, doesn't it?
Yeah.
Very directly.
And the authors didn't just rely on looking at the EEG traces visually. They also used quantitative EEG analysis, QEG. This uses computer methods to analyze the brainwave data more objectively.
Okay, the computational stuff.
Yeah, things like spectral analysis to look at the power of different brain rhythms, amplitude mapping to see where the activity is strongest on the scalp, and source analysis, which uses algorithms to estimate where the activity is likely coming from, deeper inside the brain.
And did that back up what they saw visually?
It absolutely did. This objective data reinforced the visual findings. The quantitative analysis supported the idea that the occipital, or at least the posterior region, was heavily involved. It often seemed to be the starting point, or at least showed the highest level of activity related to those eye closure events and the generalized discharges in most patients. I think it was 86% showed evidence of posterior onset or prevalence in the amplitude maps. And the source analysis specifically pointed to a predominant occipital representation for the generalized spikes they saw.
Okay, let's take a step back and think about what this all means.
Yeah.
You've got frequent focal posterior activity. You've got this pattern where it precedes the generalized discharges, and you even have documented focal occipital seizures in patients who otherwise have textbook EEM. How do the authors pull all this together? What's their big interpretation?
Well, their main takeaway is that this data strongly points to a pivotal, maybe even primary role for the occipital lobe in how EM actually works, the underlying mechanism. It's not just, passively affected by some generalized discharge starting elsewhere. They're suggesting the occipital lobe, or perhaps a network centered right there, acts as an epileptic generator. It kind of kicks off the abnormal electrical activity, which then spreads out to engage broader brain networks, including the ones we typically associate with generalized seizures.
So the occipital lobe isn't just part of the problem in EM. It might actually be the source of the problem in many, maybe most cases.
That's the compelling argument they're making, and it's backed up by both the visual and the quantitative EEG findings. They also try to connect this idea to features we already know are common in EEM. The occipital lobe's job in vision, well, that obviously links to photosensitivity, right? That light sensitivity, so typical of EEM.
Makes sense.
It might also tie into problems with the brain's alpha rhythm system, which is really important for visual processing and attention, and we know that can be altered in photosensitive epilepsies. And probably other brain areas involved in controlling eye movements are part of this network too.
Okay, so if the occipital lobe is so fundamentally involved, it kind of inevitably brings up a question that's been kicked around for a while. Are EEM and other occipital epilepsies related? Maybe even the same thing. I'm thinking specifically of photosensitive occipital lobe epilepsy, or POE.
Yeah, that's definitely been a long-standing discussion point. Because they share features like occipital involvement and photosensitivity, people have wondered, is EM just a type of PLE or maybe the other way around?
And what do Ricci and colleagues say about that relationship? Are they arguing that EEM is actually POL based on their findings?
No, interestingly, they argue against just lumping the two together. They point out that under the current ILA classification system, EM and POL are still considered distinct syndromes. Why? Because they tend to have different overall clinical pictures, maybe different impacts on cognition, and often different long-term outcomes or prognosis.
Oh, okay.
So they believe it's still important to keep these distinctions based on how the conditions usually manifest and evolve over time.
Okay, so they're not saying EM and POL are identical, but their findings show this really strong overlap in where the trouble seems to be starting, in that occipital region. How do they square that circle of distinct syndromes, but a shared origin point?
This is where they introduce a really interesting concept, which they call system epilepsy. Their proposal is that maybe EM and POL aren't identical syndromes, sure, but maybe they represent different clinical expressions, or perhaps they lie on a kind of phenotypic spectrum. And the spectrum arises from dysfunction within a shared underlying neural network that crucially includes the occipital lobe.
Ah, okay, so like think of the brain as this complex network of roads. You could have different kinds of problems on the same major highway, this occipital network, and depending on exactly how and where that network is disrupted, you might get different kinds of traffic jams or symptoms that we recognize clinically as either EM or POL, but they stem from the same basic faulty infrastructure.
That's a great analogy, yeah. The occipital lobe is like a critical hub in that faulty network, and then the problem within that network plays out clinically, leads to either the EM picture or the POL picture, even though the underlying mechanism might be starting in the same general brain area.
And why is this shift in thinking moving from seeing EM as purely generalized to understanding it has this strong, maybe initiating focal occipital part? Why is that so critical? What's the practical impact for doctors managing patients?
Oh, it's hugely practical, especially for clinical care. The authors really stress that focal seizures in patients with EM are probably significantly underestimated. Remember, patient one's documented focal seizure.
Yeah, subtle symptoms, then amnesia.
Exactly. If a doctor isn't actively looking for those subtle focal signs, or maybe if they're still working under the old assumption that EEM patients just don't have focal seizures based on the traditional criteria, well, they're going to miss them completely.
And missing focal seizures means you might not fully understand the patient's epilepsy. And maybe you're not treating it as effectively as you could be, right?
Precisely. If a patient is having these unrecognized focal seizures happening alongside their more obvious generalized events, the treatment strategy might need tweaking. You might need therapies that specifically target that focal activity starting in the occipital network, in addition to managing the generalized stuff.
So what's the call to action here? What do the authors recommend based on all this?
Their main recommendations are basically two things. First, they argue for more extensive, longer video EEG monitoring in patients who get an EM diagnosis. Longer recordings just increase your chances of catching those less frequent or more subtle events, including potential focal seizures.
Makes sense. More time, more chance to see everything.
Right. And second, and this is perhaps the biggest point, they suggest that the traditional ILA exclusion criterion for EM, that rule saying focal seizures mean it can't be EM well, that rule may need to be formally reconsidered based on this growing evidence showing focal involvement is actually common.
That's a pretty significant step, potentially changing the actual definition of a recognized epilepsy syndrome. It really underlines how important it is for research to keep challenging even established ideas.
It really does. And this research, it isn't just some academic exercise, you know? It has direct implications for day-to-day clinical practice. It could lead to more accurate diagnoses, a better understanding of what's really going on in an individual patient's epilepsy, and hopefully more effective treatment strategies for people living with EE.
So this deep dive into the Ricci paper really does unmask a surprising and much more complex picture of epilepsy with eyelid myoclonia. Those classic generalized eyelid flutters, the condition likely has this strong, maybe even initiating root deep in the occipital lobe. And those subtle focal occipital seizures and the frequent focal discharges they found, they seem to be much, much more common than the traditional definitions ever really allowed for. It directly challenges those existing diagnostic criteria.
Yeah, and what's really fascinating, I think, is how studying what seems like a very specific epilepsy syndrome can actually unlock deeper insights into the basic mechanisms of how seizure networks work, maybe even across different conditions. It forces us to think a bit beyond these rigid syndrome boxes and consider the interconnected brain circuits that are actually driving the activity.
Welcome to the deep dive. We take source material, maybe articles, research, notes like today, and we really try to unpack the key insight,
And a bit of conversation to make it stick.
EEM. And our mission, our goal for this deep dive, is to use these
Dictate how strong the evidence is and, what claims can reasonably be made based on the results.
So we're using this EEM study critique as a sort of case study.
Exactly, to help you see why looking closely at the how is so vital for understanding the what.
Okay, let's get into it. The study our source material is critiquing is called Unmasking the Role of the Occipital Lobe in Epilepsy with Eyelid Myoclonia.
That's the one.
And the notes say it used a retrospective review looking back at existing medical charts and video EEG recordings.
Yeah, video EEG, for those who might not be super familiar, it basically records brain waves, the EEG part, alongside video of the person.
So you can see what's happening physically when the brain activity changes.
Precisely. It helps link the electrical activity in the brain. Particularly, they were interested in the occipital lobe, that's kind of the back part of your head involved in vision. Link that activity to the symptoms seen in EEM. Now, our source material does say the study offers valuable insights. It's not dismissing it wholesale.
Okay.
But it really zeroes in on several, let's say, critical methodological choices, especially around that video EEG data that affect how we interpret the findings.
Got it. So let's unpack these points from the critique. First up, the study design being retrospective.
Right. So what that means is they didn't design a new experiment specifically for this research question.
They looked backwards.
Exactly. They went back through existing records, video EEGs, and charts collected between 2019 and 2024. This was data gathered during routine clinical care at the Danish Epilepsy Center.
Okay. And the critique's concern.
Well, the concern highlighted is that because this data wasn't gathered with this study-specific detailed questions in mind, there could be, variations in how the recordings were done, or maybe things weren't recorded that would have been useful for this study.
So limitations baked into the original data collection that the researchers couldn't control after the fact.
Yeah, kind of like trying to answer a really specific question using photos you just happen to take over the years instead of setting up a photo shoot designed for that question.
Right.
The why they probably did it this way, well, it's often about efficiency and access. They had this data available on a group of patients.
Practical reasons.
Practical reasons, absolutely. But the trade-off, as the critique points out, is the data wasn't perfectly tailored for their specific research hypotheses.
Okay, that makes sense. Let's move to the second point raised. The duration of the EEG recordings. The source says a minimum of 30 minutes.
Yes, and this is quite interesting because the study authors themselves actually flagged this as a potential limitation in their paper.
Oh, they did?
They did. They noted that focal seizures in EEM seizures starting in just one specific brain area can sometimes have really subtle signs, subtle ictal clinical manifestations, as they put it.
Meaning they might be easy to miss on a video or even by the patient.
Exactly. And they go on to say that because of this, the true frequency, the actual incidence of these focal seizures might be underestimated in their study.
Wow, okay, so they're basically saying we might be missing some.
Pretty much. They explicitly suggest that, and I'm paraphrasing slightly, further studies using prolonged video EEG monitoring could help get a better estimate of how often these focal seizures really happen in EM.
That's quite an admission, and it seems to directly support the critique.
It really does. The critique points out that while 30 minutes might be standard for, say, a routine clinical EEG, it might not be long enough to catch these potentially rare or subtle events needed to answer their research question thoroughly.
And didn't the critique mention an example? Patient 1.
Yes. Good point. It notes that one focal seizure was recorded in patient 1, but significantly this happened during long-term video EEG monitoring.
Implying much longer than the standard 30 minutes.
Precisely. It suggests that, hey, if you record for longer, you might indeed find more of these events. So claims about how common these focal occipital seizures are, a key part of the study, might be limited by this typical recording duration.
The why being clinical routine versus research needs again.
Seems likely. Clinical efficiency versus capturing maybe infrequent events for research.
Okay, point 3 from the critique. Sample size, just 21 patients.
21. Yeah, that's a relatively small number when you're studying a condition like EEM.
And the concern there is
Generalizability. How well do findings from just these 21 individuals actually represent the broader population of people who have EEM?
right. And the critique links this small number directly to some of the study's big claims, doesn't it?
Yeah.
Like the pivotal role of the occipital lobe or finding focal abnormalities in 90% of their patients.
Yes. Those conclusions are drawn from this specific group of 21. And this is where the critique lands a strong point. It contrasts that 90% finding with a recent large study, different researchers, different group, but still EEM, which found only about 8.6% had focal seizures.
Whoa, 90% versus 8.6%. That's a huge difference.
That's a massive difference, and it really underscores the potential issue with small sample sizes. Is the 90% finding a true reflection of EM, or is it perhaps a characteristic of this particular small, maybe highly selected group of 21 patients? You just can't be as confident generalizing from 21.
So the likely why for the small sample was maybe trying to get a very similar homogeneous group.
That's often the goal, yes, aiming for homogeneity. But the trade-off, again, is that what you find might not apply widely.
Which leads us right into the next point. The strict exclusion criteria.
Yeah, they were quite specific about who wasn't included.
The source lists things like excluding patients with other seizure types, tonic, or if their myoclonia wasn't mainly eyelids, or if they had certain genetic syndromes, moderate to severe intellectual disability, or abnormal brain scans.
Right. A lot of exclusions.
It sounds like it could leave out a fair number of people who might still be considered to have EM in a broader sense.
It certainly could. And the why for doing this, as you touched on, is usually to create that homogeneous cohort, focusing on what they define as typical EM.
Makes the study cleaner, maybe?
Yeah.
Fewer variables?
Exactly. It reduces confounding factors, other things that could influence the results. This strengthens the internal validity. You can be more confident that what you're seeing is related to the typical EM they've defined.
But, and here's the critique's point again, it limits external validity or generalizability.
Precisely. The insights, however strong for that specific group, might not apply to EEM patients who do have those other features or conditions they excluded.
Like the apple analogy you mentioned earlier, study only perfect red delicious can't claim findings applied to all apples.
That's the idea. You get a very clear picture of a very specific thing, but it's not the whole orchard. And given that there's ongoing discussion about how best to classify EM and where its boundaries lie with other syndromes, focusing only on this typical slice provides a focused view, but maybe not the full picture.
Okay, last main methodological point from the critique.
Mm.
The scope of the quantitative EEG analysis. It was limited.
Yes, it was quite focused. The quantitative part using computer analysis for measurements was done specifically on 10 consecutive artifact-free EEG epochs.
Meaning clean segments of the recording.
Right, clean segments with eye closure in the first second after eye closure.
Okay, focusing on eye closure makes sense for EM, right? That's a key trigger.
Absolutely. The why is clear. They wanted to precisely measure and characterize the brain's electrical response right when the defining feature of EEM, the eyelid myoclonia, triggered by eye closure, happens.
But the critique sees this focus as a limitation. How so?
Well, because it's so focused, it means the quantitative analysis doesn't cover all the other brain activities seen in the recordings.
Oh, okay.
So things happening between those eye closure events, or maybe other types